Some of the drawbacks of doing a Boolean overlay: we've reduced reality to simple true and false statements and values of ones and zeros. In general, the strict Boolean analysis does not really support the gradation of suitability, although we can overcome that a little bit if we comprise or compute scores by adding them together rather than doing the Boolean and. One thing that is definitely the case with both of those approaches is that we assume that all the input data sets are basically equivalent to each other. They're all equally important, and that may not be true. So this is kind of a problem that we may need to address if we are using Boolean input layers in any kind of analysis, whether it's a suitability analysis for habitat for a species existing on the landscape, whether it's a suitability analysis for where to put the next skyscraper or fire station or anything like that. Anything that we can use these rasters to analyze the environmental conditions for, we're going to face these problems with that, and there are a couple of things that we can do to modify Boolean inputs to make them a little bit more flexible. One of the techniques that we can apply to Boolean inputs to make them a little bit more flexible is to use a weighted analysis or a weighted overlay. So we can reclassify our inputs into ranked suitability values, weighting the input rasters by what we think their level of importance is for each layer. And the way to do that, here in general, we're going to define an equation. Let's calculate a generic suitability index as SI equals W1R1 plus W2R2, etc., etc. And what that means is we apply a weight to each of the input raster data sets. That's going to work out to be a multiplier. And the input raster value. So we have a weight, we multiply it by the raster value for each individual input raster. The weights that we apply to the input rasters need to add up to a value of 1. So we're using decimal multipliers, where obviously the greater the decimal value, the greater the importance of the input raster. So a 0.8 applied to a raster will make that raster more important in the analysis than a 0.1 applied to the raster. All right, so we're using that decimal place values to essentially rank them for the order of importance. So let's pretend that we are looking at an example where we're trying to find a new location for a landfill. So we're going to generate our landfill suitability index. And we have 4 different input rasters in this particular analysis. We've got slope measured in degrees, and we've put those into different classes. So slope from 0 to 10 is in the value of 3, 10 to 20 has a value of 2, greater than 20 has a value of 1. It has a weight of 0.1. Infiltration, low infiltration, score of 3, medium, score of 2, high, the score of 1, 0.4 on that. That's really important. We want to prevent chemicals and things in the landfill from infiltrating into the water table that's underneath it. Distance to the roads in meters. Here, again, we've created a score for it. 0 to 500 meters, 3, 500 to 1,000, 2, greater than 1,000 is 1. And our weight, our multiplying factor is 0.2. Distance to streams in meters, 0 to 100, 1, 100 to 200, 2. Greater than 200 is a 3, multiplied by 3. So our LSI land suitability index equation is 0.1 times slope plus 0.4 times infiltration plus 0.2 times road distance plus 0.3 times stream distance, resulting in suitability scores ranging from 1 to 3. So there's an example of how we can do that. We can apply our input values, reclass them in this case to something else, to a value that makes sense for some reason, different classes of the different data categories, the different data types, our variables, and then apply those weighting factors that give us an idea of how important they are. And we get those typically from folks that are experts in whatever analysis we're trying to do. Someone that needs to be really familiar with soil properties and environmental conditions here to gauge the importance of the different variables and apply these different weights to them, so that our final analysis says, yeah, these are locations that meet our input criteria, meaning they're low infiltration, low slope, close to roads, and far away from streams. So we can combine both of those different approaches, our generic suitability index, and we can apply then Boolean rasters to that. So if we were calculating the example from before of the landfill suitability index, and we have that particular equation, we could then apply to it Boolean rasters of true and false information to further modify the results. So what this does, in effect, is it sets off-limits areas or zones where we absolutely will not consider for analysis. In those Boolean grids, those are the zeros. And so those areas fall out of the analysis when we evaluate the equation. Basically, when you create the equation, you include those Boolean rasters. Remember, they're multiplicative, or they're going to act as multipliers. So 0 means the cell value coming out is 0. We know that if a cell has a value of 0, that's not a location we're going to choose in any way out of that suitability analysis. It is not suitable for our purpose. So here is a great kind of an example. Let's say we have people that are interested in purchasing property. They want to build a cabin out in the woods somewhere. And so we conduct a landscape analysis using slope, aspect, land cover, vegetation types, maybe some other things, other conditions, temperature and precipitation, maybe snowpack, stuff like that. Whatever it is that we use, we conduct an analysis, and we've got a score on the landscape for this entire area. However, the area also contains federal Forest Service land, which we cannot purchase. It will not be available to us to purchase. So we use a Boolean layer in the analysis at the end, after we've done the primary analysis. Then we apply this in the equation. It's just maybe the last thing that gets done. And since we're multiplying by ones and zeros, all the ones don't change our scores at all that we've calculated first. But everything that was a 0 falls out of the analysis, and we say, all right, here in gray is Forest Service land that has a value of 0. Those are areas that no matter what their score was, we simply can't buy it, so it falls out of our analysis entirely. Here's what your map algebra interface looks like. The raster calculator, found in our toolbox, spatial analyst tools. Underneath map algebra, we have the raster calculator. And all the things that we've been talking about using, you can apply using the raster calculator here. It will show you the valid grids and rasters that you have available and allow you to apply a whole range of different kinds of operators, the strict numeric operators and Boolean operators that we see on the buttons. And then there's also that scroll bar on the left, which has a lot of other operators in it that you can choose to apply to your raster data sets in equation form. And then, of course, you always specify where your output raster data set is going. We always need to keep track of where those things are going, no matter what. Whether it's raster, vector, anything, your best practice is you're always keeping track of it, and you're marking it in your log when you are doing something for a project. You keep track of what you put into the raster calculator, what you did to it, and what you called the output, name, and where it was stored. And if it's a Boolean, what that Boolean logic actually means. What does the 1 mean, and what does the 0 mean? What's the condition that you used to create that data set? Recall that ArcGIS allows you to put certain things in place, the environment settings that modify or control your outputs when you're doing different analytical techniques. On the left, if we're using the menu option for geoprocessing, the environment setting there is global. At the application level, it applies to all of the tools and menus that you choose to deploy and use in your analysis. And on any given tool, graphic user interface, any GUI window, you have access to the environments tab there as well. And that will affect the single execution of that tool when you call it up. So you can set your settings at the beginning of a project, or as you call up individual tools, you can modify the settings there. And it applies to that single operation. Some of the ones you may want to explore using, if you haven't already, from earlier in the course. Looking at your workspace, setting where your Scratch workspace is, basically your data dump area for temporary files, where you want your outputs to go, the processing extent, or using data sets to constrain the output to a certain area. And under raster analysis, we have things like specifying cell sizes, applying analysis masks, and some other things, and we'll take a look at what those are a little bit later. So your working directory and environment settings, your current workspace, that's where things go. Your Scratch workspace is where temporary files will go. If you're someone who forgets to put things in the right place all the time, environment settings can be a godsend, and they can put things exactly where you want them to be during that particular project. It's something you need to set every time you start a new map document or other similar document in other modules of ArcGIS. Another setting is for your output coordinates, the output coordinate system. As always, grids are best stored in projected coordinate system for analysis for lengths and areas and things like that. So we always want to have projected rasters. Unless you otherwise specify it in your analysis, the output is going to match the first raster input to the tool. Automatically, outputs will be resampled to the coarsest resolution or what you specify, and maybe reprojected during the analysis if it's needed to be done, if it hasn't already occurred, in order to match. Both those processes are done basically on the fly to match cell size, resolution, and projection systems. Something to keep in mind is that if you haven't done the best practice of projecting all of your data before you do your analysis, The constant projection that you're doing using the tools may degrade your accuracy and data, and therefore you may introduce errors into your outputs. So your best practice, once again, is to keep all of your data sets, both the inputs and the outputs, in the same coordinate system. And you do that first, ahead of time, before you conduct your analysis. You decide on your common coordinate system that will be used for the project, and everything is reprojected to match that. If you use the setting, data frame coordinate system should match the coordinate system of your data sets, which is great. So, as always, when we're doing analysis, you must be aware of what you're doing. As the little block of text says, be mindful, not oblivious. Understand what it is that you're doing. Understand what it is that the system is going to do with your data when you call up any particular procedure or analytical technique, and what it's going to do to your outputs. What kind of outputs are you going to get? And then check those outputs to make sure that they are contain the values that you expect from that particular analytical procedure. Another powerful setting is that for processing extent. Up above in the two figures, we see two examples, union of inputs and intersection of inputs. So union of inputs would be the larger bolded zone, and that includes the area of all of the input polygons in that case. That's what gets output, is all that. The intersection of inputs would be only the common areas between all of the input layers. So the smallest of the input data sets controls what gets output, and it constricts it to that, just like a clip operation. But you're applying a clip during the analytical procedure. The union is all possible polygons together. Their complete and full extent becomes your output. Down below, we're seeing examples of you can specify the processing extent to be the same as whatever's being displayed right now. The total of all those things, again, kind of like a union in some ways, or same as any particular individual data set. So same as the elevation data set. If we wanted to use that data set as a clipping layer, that does it here. Okay, so intersection of inputs gives you the smallest of all possible polygons as the clipping layer, or specifying individual data sets to use as the clipping layer. A critical setting to be aware of in the environment settings is the cell size. Best practice for raster analysis, as we've covered before, is that the coarsest cell size determines the output cell size. So by default, the cell size option will be the maximum cells of all of the possible inputs. If you haven't already resampled your data, ArcGIS will do that by default during your analysis. Or you can specify particular layers if you need to for your analysis. But the best practice approach, and the one that I expect to see in any work done with rasters, unless it's otherwise specified, will be that the coarsest input data set cell size controls and determines what the output grid cell size is going to be. An analysis mask works like a clip, but it works during your processes. So imagine that you have a number of different things that you're going to do with different data sets that have different extents, but you're only interested in a common area of all of those inputs, your study area, and you want to clip everything as you do your work. Well, the analysis mask allows you to do that for polygons or for rasters. So the input will be a data set. For polygons, you specify a polygon mask. There you go, and apply that, and then your output is restricted to the maximum outline of the polygon. If it's a raster, we create basically a Boolean data set, ones and zeros, or ones and no data, and apply that to all of the rasters in the analysis. It constricts all of the outputs to the study area, and the polygon mask does the same thing. All right, so it's something that you can set ahead of doing your analysis if you have a common area that is your study area between all of the inputs, and you're restricting all of the techniques that you use. All the analytical techniques will be restricted in their output to be contained within that study area, and it will exclude all other area from your outputs. So one of the things we may want to do when we're conducting a project is to extract information from a raster, essentially clip it. There are several different ways that we can do that. One of them is to use the tool that's dedicated to that task, extract by mask. And so we create a raster mask, a Boolean of ones and no data, apply that to the data set, and it extracts, and your output is only whatever your input mask was. Okay, so where there's valid raster cell values in the mask, that constricts and cookie cuts the original input data set, and then you get the output, which is just your study area. So it functions very much in many ways just like applying a clip with vector data. Although we create the mask data set somehow using different procedures, it's not the same as creating a buffer around things. You have to manipulate the values in order to create that mask and apply it.